Welcome to lesson 4, which is on Dalton's law of partial pressure and Graham's law of diffusion. If you're keeping track, we have completed 4 laws so far, and we're adding on 2 more today. So, as you remember, we had Boyle's, Charles, Gay-Lussac's law, and in our last video, we learned about the ideal gas law. Today, we'll have 2 new laws. Dalton's law of partial pressure, which combines the individual partial pressures of a combination of gases to give you the total pressure, and Graham's law of diffusion, which talks about how fast a gas travels in comparison to other gases. So first, let's take a look at Dalton's law of partial pressures. If you look behind me, the total pressure of a system of gases is equal to the partial pressure of the individual gases that make up that system. So imagine you have 3 different gases, gas A, gas B, and gas C. And let's say they have partial pressures of 2 atm, 3 atm, and 4 atm. If I were to take these 3 different gases and combine them into a single container, all mixed together at the same time, their total pressure would be equal to the sum of their partial pressures. So the 2 from gas A plus the 3 from gas B plus the 4 from gas C. In this case, we would wind up with a total pressure of 9 atm. Dalton's law is really that simple. Now, I've created a few example problems to illustrate what a problem might look like when you see it on a quiz or test. Let's take a look at example 1. It says you have a container that holds 3 gases, oxygen, carbon dioxide, and helium. So remember, oxygen would be O2, carbon dioxide would be CO2, and helium, of course, is just an element in its most simple form. The partial pressure of oxygen, we are told, is 2.00 atm. So partial pressure of oxygen equals 2.00 atm. The partial pressure of carbon dioxide is equal to 5.00 atm. And we're told that the total pressure, or P total, is equal to 13.00 atm. That leaves one gas, helium, as our unknown. So in this case, if you know the total pressure, and there are 3 gases, and you know 2 of the 3 gases, you can subtract to find the pressure of the last one. So together, these 2 add up to be 7.00 atm, meaning that our partial pressure for helium, in order to get to 13, would be equal to 6.00 atm. Again, not a very difficult question, but it's a simple law to begin with. Let's take a look at a second example. In our second example, we are told that we once again have 3 gases, and they are confined to a container. This time, the gases are just referred to as A, B, and C. We're told that the partial pressure of gas A is twice that of gas B. So the partial pressure of gas A is equal to, so here's gas B. We don't know what that is, but we do know that A is equal to 2 times the partial pressure of gas B. Finally, we have a third gas, gas C, which has a partial pressure of 0.5 atm. They tell us that the total pressure of the entire container is equal to 5.00 atm. That means all 3 of these gases, when we find their individual pressures, will add up to give us our 5.00 atm. Now, our goal is to find the individual pressures of gases A and B. So to do this, what we want to first do is subtract out from the total the one gas that we do know, which is gas C. So our formula will look like this. P total equals the partial pressure of A plus the partial pressure of B plus the partial pressure of C. Well, we know that the total pressure is 5 atm. We don't know the partial pressure of A or the partial pressure of B just yet, but we do know that C is equal to 0.5 atm. So just like you would do in math class, we're going to subtract C from both sides to essentially move it to the left side. So at this point, we now have two variables left, and we now know that the sum of just those two is going to equal 4.5 atm. Now, the problem did give us one other important piece of information. Even though we don't know what the partial pressure of B is, we do know that the partial pressure of A is equal to twice that of B. So we can replace the variable that we have identified currently as the partial pressure of A with 2 times the partial pressure of B. Believe it or not, this is a really simple problem to solve. Now, it sometimes confuses students because we're using pressures instead of terms that they're more familiar with, like X. So imagine that instead, you were in math class and you had 2x plus x. Well, you would say that's equal to 3x. But in this case, since we have partial pressure of B, we're going to say that's equal to 3 times the partial pressure of B. If 3 times the partial pressure of B is equal to 4.50 atm, then I can simply divide both sides by 3 to get the partial pressure of B equal to 1.50 atm, or the result of taking 4.50 and dividing it by 3. The last piece of this is to recall that our partial pressure of A is equal to twice our partial pressure of B. So if our partial pressure of B is 1.5, our partial pressure of A is going to be equal to 3.0 atm. Remember, together, these two had to equal 4.50 atm, which was the missing piece that we had over here. All right, so that is about as difficult a Dalton's law problem as I can come up with. Now let's take a look at Graham's law of diffusion. Okay, looking at the screen behind me, we see Graham's law of effusion. First of all, what does it mean for something to effuse? Well, when we're talking about gases, effusion refers to the process where gas passes through pores, almost like pores in a balloon. Now, Graham's law of effusion talks about how fast that process occurs and is usually used to compare the effusion of two different gases. When we solve Graham's law problems, we'll end up solving for this ratio. So we won't identify a particular velocity of a gas. Instead, we'll say that one gas escapes or effuses 3 times faster, twice as fast as another gas. In order to make that comparison, we need to look at their individual molar masses. And in this equation, MM that you see underneath the square root sign refers to the molar mass of the two different gases that we're comparing. Just make a mental note. When you're performing this calculation, it works out best and easier if you always put the heavier gas on top. So in this case, we have molar mass 2 and molar mass 1. Please remember to put the heavier gas on top. When you do your calculations, you'll wind up with a number that's greater than 1 that you can use as part of your explanation. let's take a look at what this would look like in terms of an actual problem. So we're going to look at a chemical reaction that occurs between ammonia gas and hydrochloric acid, which is also a gas when not dissolved in water. So in this case, notice that we have this kind of container where the gas is going to be introduced on opposite sides. Imagine almost like a clear plastic tube. Well, it turns out that these two gases, when they come together, will produce this solid. And the solid appears to be a white cloud when the two gases interact. So my question to you is, will that white cloud form right in the center of the tube? Will it form closer to the left side, or will it form closer to the right side? Well, think about this. The heavier a gas is, the slower that gas effuses. So if you think about the molar masses, the molecule that has the smaller molar mass is going to move around faster than the molecule that has the larger molar mass. So in order to answer this question, we must first calculate the molar mass of each of our two reactants. So ammonia, which has a molar mass of 17.04 grams per mole, is going to be faster than our second gas, hydrochloric acid, which has a molar mass of 36.46 grams per mole. By now, you know that those numbers are obtained by looking up their molar masses on the periodic table. Okay, so if in fact the lighter gas travels faster, then in the same amount of time, the lighter gas is going to be able to travel further than the heavier gas. So the answer to the question is, if ammonia with its lighter molar mass travels, it's going to make it further along in the tube than hydrochloric acid with its heavier molar mass. So that means the white cloud will form closest to position C. Now let's take a look at two example problems to see how you would perform these calculations. So in example number one, we have two gases, water and hydrogen. So water, remember, has the formula H2O and has a molar mass of 18.02 grams per mole. And hydrogen, which is a diatomic, has a molar mass of 2.02 grams per mole. So looking at my equation, keep in mind, we're solving for this as one thing. So our ratio of rates is equal to the square root of molar mass 2 divided by molar mass 1. We're going to put water on top because it's heavier. So we're going to have 18.02 grams per mole on top. And then on the bottom, we'll have the molar mass of hydrogen, which is 2.02 grams per mole. Now, the first thing that I want you to notice is that the unit of grams per mole is going to drop out. So our answer will in fact be unitless, meaning it doesn't have a unit. Next, we can divide our two numbers, 18.02 divided by 2.02, to get an answer of 8.92. And finally, to get our final answer, we'll take the square root of that number. So in our case, we wind up with a final answer of 2.99. Now, what does that number truly mean? So when we're doing a Graham's law of effusion problem, our final part will be a statement that explains the significance of the number that we just calculated. In this case, we're going to say that hydrogen travels 2.99 times faster than water vapor. And there you have it, your first Graham's law of effusion problem. Now, let's take a look at a second example. This time, we're going to calculate one of the molar masses. Okay, taking a look at problem number 2. It says hydrogen is trapped in a container with an unknown gas. Hydrogen effuses 2.82 times faster than whatever this unknown gas is. And they want us to calculate the molar mass of this unknown gas. So we're going to use our formula V1 over V2 equals the square root of M2 over M1. But this time, instead of solving for the ratio of rates, which we're given in this case as 2.82, we're going to be solving for one of the molar masses. So we have hydrogen, which, as a reminder, has a molar mass of 2.02 grams per mole. And we have an unknown gas. Based on the statement that hydrogen travels faster than whatever our unknown gas is, we know that the unknown gas's molar mass has to be greater than 2.02. This is also important when we place our variables in our equation. So V1 over V2 equals the square root of molar mass 2 over molar mass 1. This was given to us in the problem. This is equal to 2.82. So now we have to place our molar mass 2 and our molar mass 1. Remember that our heavier gas should go on top. In this case, our heavier gas is the unknown. So our unknown with its unit of grams per mole is going to be on top. And on the bottom, we're going to have our 2.02 grams per mole molar mass of hydrogen gas. Now, think back to your math class. In order to get rid of a square root sign, you square both sides of the equation. So the very first thing that we're going to want to do is take our 2.82 and multiply it by itself to get an answer of 7.95. That will get rid of the square root sign that we had on the right side. So we'll now have our unknown over 2.02 grams per mole. Finally, to solve for the mass of the unknown, we're going to cross multiply. So we'll have 2.02 times 7.95. That'll give me an answer of about 16.06 grams per mole as the mass of our unknown. Now, in this case, there's an additional question. They give you a selection of choices on the right side, and they ask you to identify what gas this is. So to do this, you need to find the molar masses of all of these different gases and find out which one has a molar mass closest to our unknown. So looking at these, we have 12.01 plus 32. This is 44.01 grams per mole. That's not close to 16. So it's not going to be carbon dioxide. In our next example, we have sulfur dioxide. Sulfur is 32.07 plus 32. So we have about 64.07 grams per mole. Again, that's not close enough to 16.06 grams per mole. In our third example, we have 12.01 plus 4.04 for a total of 16.05 grams per mole. That's really close. 16.05 versus 16.06, chances are this is going to be our final answer. Let's take a look at the other ones. We just calculated ammonia in a previous example. That was 17.04 grams per mole. Chlorine gas would be 70.90 grams per mole, or 2 times 35.45. And finally, N2 would be 28.02 grams per mole. So it's definitely not nitrogen, chlorine. And although ammonia is close, it's not as close as CH4 or methane is. So I would indicate that methane is the final answer in this problem. Okay, I would like you to try the homework problems on Graham's law and Dalton's law of partial pressures. Please let me know if you have any questions and stop by office hours. Thanks very much, everyone. Have a great week.